Good afternoon, ladies and gentlemen. Before I start, I would like to acknowledge the contribution of my colleagues. Actually, they are those that have done the work. I'm just presenting here. Andreas Theodorakakos and Richard Pearson and Martin Gold from BP that have co-authored and sponsored this work. So let me start with the motivation of this work, which is part of a greater plan. I guess all of us, we know that diesel oil consumption on the commercial sector is going to increase a lot over the next 2 decades. Many forecasts suggest that. And it's also already an industrial reality that that demand will be met from different oil sources, including the conventional but less conventional ones. So that macro trend that is here affects what we do in different ways. If we narrow down first to fuel systems, we know that the various properties do affect nozzle flow and cavitation, but the actual influences are not fully understood. And if you narrow further down to what we do in computational studies, most of what we have seen so far in the literature refers to simulations that constant properties are frequently utilized without taking into consideration the variation as function of pressure and temperature during the depressurization of the fuel as you go from the rail to the injector. And on top of that, if cavitation is taking place, we know and we have seen during the last 2 days that it does have an effect on flow rates and erosion and overall the system performance. So the objectives of and the aims of the present work are the following. The first is to try to simulate the effect of variable fuel properties on nozzle flow and cavitation as we depressurize the fuel from the rail to the nozzle exit. To investigate how different fuel components cavitate for a range of conditions, pressure and nozzle designs. And once we have quantified those effects, to compare how they are close or far from changes to the nozzle flow that can be introduced or induced by simple modifications to the nozzle design, like the tapering of the nozzle or a radius of curvature, things like that. How I'm going to address those objectives, this is the structure of the presentation that is going to follow. I'll give an overview of the model that we have been using for this study and a description of the nozzle configuration that has been utilized. I'll go then through the various results, which briefly cover the effect of variable fuel properties, both for fixed need lift and variable need lift cases. I will show the effect of cavitation, and I will show the effect of fuel composition. And at the end, I will summarize with concluding remarks. So I will start with a very brief introduction to the CFT methodology, similar to what my colleague Fivos Koukouvinis presented yesterday. At this stage, we decided to keep things relatively simple, and in order to have a first order of magnitude comparison between the different cases, we don't consider it was necessary to go to more complex LES or other simulations, so runs have been adequate for this study that you are going to see today. Cavitation, again, as it was mentioned yesterday, is treated on a Eulerian-Lagrangian approach, that cavitation starts from pre-existing nuclei in the fluid, that they follow the Rayleigh-Placet equation, and then we calculate their interaction with the flow with appropriate interaction terms in the solved equations. In addition to those, which are kind of standard, we have introduced the enthalpy equation. So that's also fully coupled with the cavitation, and in which we consider variable fuel properties. So density, viscosity, heat capacity, thermal conductivity, and internal energy are all function of the specific fuels that they are used. And these vary throughout the solution in every single computational mesh cell as we calculate. In terms of the fuels that we have used and we are going to see in that presentation, I'm going to use 2 examples, what we refer to as heavy and light fuel. And heavy and light actually, I should say, more viscous or less viscous. As you can see, the density variation for different pressures and temperatures between the two does not change that much. What does change is the viscosity and the vapor pressure. So notice the logarithmic scale on viscosity. So as we increase temperature and during the depressurization of the fuel, that can increase significantly, as you will see in a minute. There is a significant change of viscosity. It can change almost an order of magnitude. And also notice that between the two different fuels, what I refer to as heavy and light, have a different variation of viscosity across the temperature range that we are investigating. That will have some effect on the results that you are going to see following. In terms of the studies that I'm going to present, starting from a typical 6-hole injector, we are simulating only symmetry, a sector of 60 degrees, applying symmetry boundary conditions, adiabatic walls, a range of injection pressures from 1100 to 3000 bar, a fixed back pressure of 60 bar, and we also fix the fuel inlet and initialization temperatures to 80 degrees for the studies that I'm going to present today. In terms of, if we look to a little bit more detail to the nozzle flow itself, we are using a radius of curvature at the whole inlet, and also straight holes and some tapering in order to have more or less cavitating flow conditions. I should also mention that during the transient motion of the needle, the minimum lift that we have applied goes down to 1 micrometer. So before getting into too much detail, that's how it looks like. It's very much a simple nozzle, nothing exceptional is happening, not too complex flow regimes. Cavitation is concentrated only on the upper part of the injection hole, and we have specifically selected that in order to have a first feeling of some important effects rather than going to very complex flow structures that may appear in more complicated injector designs. So I will start presenting the various results, and I will start, and the first one is something which is, let's say, the simplest case. On the horizontal axis, we have the nozzle discharge coefficient. The vertical axis, the temperature difference between the inlet and the exit. And effectively, you see that as a function of the discharge coefficient, one can calculate by simple zero-dimensional thermodynamic considerations the temperature increase of fuel. One means that all pressure is converted to kinetic energy. 0 means that all pressure is converted to enthalpy, and therefore you can calculate from the properties the corresponding temperature increase. The different, the lines, the continuous lines represent simulations performed from a 0D model, and the points that are superimposed are from the CFD simulations. So we know that once you have the properties into the solver and you calculate friction, the heating to get, the overall heating, is what you should expect from theory. Those simulations are initially performed from some, assuming single-phase flow, and then if you add on top of that a cavitation, which can take place, we see that that does not play a significant role on the heating. So you expect some interaction because maybe the flow rate changes, but mainly that effect on heating is small. Now, let's take a step further and see how the different fuel components that you may consider in the fuel may affect things. And what I'm presenting here is the effect on fuel delivery. So starting from that reference case, the blue bars correspond to the light substance, the red one to the heavy substance. So starting in a normalized way from 100%, which corresponds to fixed properties and single-phase flow, we know first of all that the difference in viscosity does affect the the mass flow rate, and that's because of the difference in viscosity. Density is more or less the same, so it's mainly a viscosity effect. Then you can apply on that the cavitating phase, and you find, as you expect, overall a reduction in fuel delivery. All those simulations are assuming constant properties. The next complexity is to add the variable properties, and what you find here is a slightly different trend. The light component gives predictions that relative to the reference case show a reduction, while the heavy component has a different trend. And that's a balance between the variation of density and viscosity across the range of the operating pressure. So depending on which component you have, you may find a different variation there. If you, on top of that, add the cavitating phase to the simulation solution, then you don't expect to see a significant variation in terms of trends. You just see a reduction as you would see in the constant property simulations. So the conclusion from that is that depending on which fuel you have and which property that fuel has across the range of pressures, you might find different kind of mass delivery through the nozzle for a given pressure difference. Another measure of quantifying the effect of properties on nozzle and cavitation is to compare for the heavy and the light fuel, which are to the left and to the right, the bars, the area at the nozzle exit occupied by cavitation. I refer to that as blockage. Effectively shows how much is the volume of cavitation that exits through the nozzle. So in that case, it goes up to 12%, the remaining 88% is the liquid that comes with it. If density was constant, that would automatically translate to a corresponding increase in injection velocity. So what we see here is that the effect of properties is more profound on the light components, and in relative terms is less when you consider variable properties. The previous case I presented referred to fixed needle lift at a given, say, maximum value or across the range. Now let's see how things may change when you have an actual transient needle lift profile, and that's what we have assumed for those simulations, something which is, let's say, an assumption for these cases. It goes from 0 to 1 millisecond. What I'm presenting with the two different colored lines now is the temperature increase, as I was predicting before for the fixed needle cases, but through the injection event. So the temperature increase of around 20 to 30 degrees at time around 0.8 milliseconds, which is the flat part, the maximum needle lift case as it goes in the previous cases, corresponds to what we had before. However, during the opening phase of the needle, we see a disproportional large increase of fuel heating. That's caused because of the flow through the narrow needle sheet passage. And we also see that as you increase pressure from 2,000 bars, let's say, to 3,000 bars, the temperature increase is becoming even higher. If you add the second phase on those simulations, again, as one should expect, the temperature, the overall temperature increase isn't that much. An interesting comparison is this one. In that case, I'm replotting the same simulation results as before, but in that case, the horizontal axis is not time, but is the needle lift. So as you go from left to right, it's the upper part of the curve, so it's the opening phase, and then as you return is the closing phase. So you see a difference in the heating caused during opening and closing, and you see that the spots which are in between of those two lines for the two different pressure levels are the corresponding predictions that have been performed to the equivalent fixed needle lift case. To the animation to the left, it's something which I'm not going to say too many things, but the importance of that is that it's not only the average temperature increase and the overall heating, but the actual temperature distribution that is formed within the injection hole orifice. And you can find a very strong temperature gradients, and if one look to the actual scale, you may find locations across the surface of the nozzle that you may overcome boiling points, so you may have more complex effects happening. Some of the colleagues here, I know that they are looking to that part of design in more sophisticated ways, so they are solving the conjugate problem of heating between the liquid and the solid part of the metal of the injector in order to have more appropriate boundary conditions for the temperature, for the heat transfer. Now let's see on top of that how the different composition may affect the results. And I'm using for those following simulations some more moderate pressure values for the two different components that I have simulated. If you were fast enough, you would be able to see that between the light and the heavy components, cavitation was starting much faster for the higher pressure case, and going towards this direction was the less, the slower developing one. If we want to quantify those simulations, I have this graph, which is what I presented before for the blockage area, so how much is the amount of cavitation area occupying the nozzle exit area. And I have the 4 different curves which correspond to the 2 different pressure levels and to the 2 different fuel components. The curve to the left, so this one is the heavy fuel, which shows to cavitate much slower, while to the right, while to the left it's the light one that cavitates faster. So for a given fixed, say, pressure level, 1500 bar or 1100 bar, can correspond to some pilot, let's say, injection events. You see a difference in the initiation and the development of cavitation growth that in relative terms corresponds to a rail pressure difference of 400 bar. You can get the same by adding pressure by 400 bar. Those simulations refer to a straight injection hole, and you can notice that after that initial period of cavitation initiation, all of them more or less converge to the same 12%, 10-12% value. The next slide, which is this one, and is the last result I'm going to present, refers to some predictions for a fixed injection pressure, 1500 bar in this case, but we have mixed together straight injection and tapered, straight injection holes and tapered injection holes. So the top curves refer to the straight ones, cylindrical, and the lines below that refer to the tapered. Again, we have with the red, the heavy component. So that line to the right is the tapered, the slower one with the less cavitation is the tapered nozzle with the heavy fuel. The other extreme is the straight hole with the light fuel. And you can see again that the same trend as it was presented in the previous slide is also apparent in that tapered nozzle. What is also interesting to see is that on top of those simulations, we have added some cases in which we introduced to the heavy fuel a small percentage, say 1% of the light one. And because it's volatile, that's the one that cavitates. And you can see that the lines that were initially the red ones have become the green ones, which are very close to the behavior of the light fuel. So summarizing, I presented some results which have considered variable fuel properties in simulations for nozzle flows and have captured the heating effects. And we found that the prediction of fuel delivery, once you are a CFD engineer, you want to know how much is injected, is strongly affected by those assumptions that you make for those simulations. We found that the cavitation inception for lighter fuel components is faster, and it changes as function of the needle opening time and closing time. And the time scale of this event is comparable to valve opening. It's about 0.1 millisecond, which for today's trends, it's equivalent to what it takes for a needle valve to open. We also found that that is comparable to some variation in total amount that can be of cavitation that can be produced by changing the hole tapering or the nozzle hole radius of curvature at the inlet that I have not presented, but we know it does affect the results in a similar manner. And we also demonstrated that the injection pressure affects cavitation, and the variation of fuel properties has an effect across the range of values that they were tested. So I will close with that, and thank you for your attention.